triagram I posted will be is a typical example of a question you guys will see in the exam. Okay, that's a typical. In short, it will be the same question. Let me just put it that way. It will be exactly the same question. What will only differ will be the molecular formula of the compound and the spectra. That's only what will differ. So understanding how to work this problem out will be a great advantage for you guys to prepare for the exams. Is that okay? And again, I'm recording this class as always, like I record all the classes. So if you want to go back, and revisit it, you are welcome to do that. And you are encouraged to do that. So in this particular problem, I guess you guys have a copy of the problem. So it might not be visible for those who are right at the back. But I guess everyone has a copy. So for this particular problem, we are giving different spectra. We're giving an IR, we're giving a proton NMR, we're giving a carbon NMR, we're giving a depth 135, we're giving a COSY, and we're giving a head core. And we are asked to use all those spectra in order to determine the structure of a compound with molecular formula C4H8O2. Okay. And here we're given a template, a table to fill in the information. So basically we have to use all the spectra, extract information from those spectra, fill this on the table, populate the table, and from there come out with the structure of the compound. That's basically what the question is all about. That makes sense? So the first table we have to fill is the IR spectrum. Okay, so we have to fill the IR. That's table 1. That's the first thing we're doing, working on the IR of the compound. So I will open my IR spectrum. That's the IR spectrum of the compound over there. Okay, and I need to fill it. Remember that the molecular formula for the compound is C4H8O2. Does that make sense? And when searching for the IR spectrum, I have 2 oxygens here. So 2 things come in mind. It can either be an ester, or it can either be a carboxylic acid, or it can either be something with 2 alcohols, or with 2 ketones. We need to find out. Does that make sense? And so we need to proceed by elimination. If we suspect the presence of an OH, then we expect to see a signal around 3500. Does that make sense? And in this case, around 3500, we don't have any signal. But we can observe a strong signal around 1700. Do you see that? We can observe a strong signal around 1700. And we can also observe another strong signal here around 1200. Does that make sense? Those are the 2 strong signals of interest. So all you need to do now is go back to your table and fill them. So I have a frequency. Well, try to give me the exact value, okay? Try to be exact as possible. I don't know, maybe, 1710. I'm trying to be exact. So on my table, I have a frequency of 1710. And from my table of references, that's my table of references. From my table of references, whatever, here. (1710) will probably correspond to the presence of a carbon double bond oxygen. Does that make sense? 1710 corresponds to the presence of a carbon double bond oxygen. So under the section that says bond, I will put a carbon double bond oxygen. Does that make sense? Now, from the IR, we're able to see another frequency around 1200. And if we double check our table, the frequency around 1200 imply carbon single bond oxygen. Okay, so go back to the table. Frequency around 1200 implies a carbon single bond oxygen. Does that make sense? Okay, so I'm good with that part of the table. Now, there's a section that says functional groups. So it means that here we are still suspecting, okay? We are still suspecting if we have several functional groups. So functional groups indicated from the infrared spectrum. So from my infrared spectrum, most likely the functional group I have over there is an ester, meaning a carbon double bond oxygen and a single bond oxygen. Okay, so technically from my IR, that's the partial structure I can guess from the IR. Okay, that's the partial structure I will guess from the IR. Are we good up to this point? Are we good up to this point with everyone? Now we'll move to the next spectrum. The next spectrum is the proton NMR. The next spectrum is the proton NMR. So that's what the table says. So let's go to the proton NMR. Let me look for my proton NMR. This is my proton NMR. You guys may not see it clearly, but I guess all of you have a copy. Because I emphasize that you all should have a copy. It might not be very clear. Now, my proton NMR, just the same thing as we usually do, right? We have basically three set of signals. You should know what that means already. It means you have three different types of protons in the molecule. And then you have to label your spectrum. You must label your spectrum to make things easier for you. And in this class, we've agreed that the chemical shift closer to 0 will be labeled A. So this will be labeled A, and this signal will be labeled B, and that signal will be labeled C. Does that make sense? So A, B, C. We have to go back to our table and match that under signal identifier. The column that says signal identifier. So we'll have a signal A, signal B, and signal C. Okay? So those are the three signals. So what's the chemical shift for signal A? According to my table, the chemical shift for signal A is about 1.211. Is that okay? So that's signal A. The chemical shift for signal A, that's it there, over there. So take the middle value. You can take the first or the last value, any of these values. That's fine. So I will take the middle value just to be fair. 1.211. That's the chemical shift for signal A. What about B? What's the chemical shift? Huh? 1.99? It's 3 decimal places. What's the third figure? C. What about C? Oh God, you guys should participate. 4.081. So that's the chemical shift of C, right? Now let's go to multiplicity. What's the multiplicity of A? A is a triplet. What about B? C. What's the multiplicity of C? Someone said it. I heard it there. Thank you. Quartet. Is that okay? Multiplicity of C is quartet. Now, the integration unit. Integration of A. 128.05. Do you see that? That's the integration. Okay, integration of A is 128.05. So 128.05. What about the integration of B? And C, 81.7. Are we good up to this point, guys? Yes. I am on the table that says proton NMR. The table is directly below that of the infrared. Yes.
How come C is a quartet, but it only has two
No, the number of the values, the chemical sheet you see down there, you know, it all depends. I could give you all the four, I can give you just one, I can give three, you know, it all depends. Okay, what matters is the number of peaks you see there, is the quartet. So because you see 4 peaks there. See, it doesn't have to do with the number of, because the number of chemical sheets that I put down there is an registration. I put the number that I want. But the number of peaks there is not a registration. The signal gives you that. Is that okay? Are we good up to this point, guys? Okay. Now, yes. No, okay. We have to fill the next column, this one. We have to fill this one. Number of hydrogens. Where do we get the number of hydrogens from? We get the number of hydrogens from the integration. Does that make sense? We get the number of hydrogens from the integration. So we have to do that. And here now, the problem is this. The integration, the sum of the integration is not equal to the number of hydrogens in the system. And so we have to do the math. Does that make sense? Remember, if the sum of integration equals the number of hydrogen in the system, then the integration of each signal corresponds to the number of hydrogen of that signal. But because the sum of integration, 128 plus 126 plus 81, that doesn't equal 8. Remember, we have 8 hydrogens in the system. And so because it doesn't equal 8, it simply means that we have to do some math in order to get the exact number of hydrogens. Does that make sense? Okay, so the first thing I want to do here, I will do my sum of integration. And that sigma stands for sum. So the sum of integration will be given by 128.5 plus 126.52 plus 81.7. What do we have? Sum of integration. Do the math. I don't have my calculator. Three 336.27. So that's 0.24, 0.04. Huh? 27. Okay, I will go with 27 then. Thank you. So the number of hydrogens for A, the number of hydrogens for A will be given by the integration of A, which is 128.05, divided by the total, the sum of integration, multiplied by the number of hydrogens in the system. The number of hydrogen in the system is known to be 8. Does that make sense? So when you do the math, what do you have? How many? Gracias, mucho gracias, señorita. B, 126.52 divided by 336.27 multiplied by 8. What do we have there? And C, 81.7 divided by 336.27. What do we have? So number of hydrogens, 3, 3, 2. Yes? I just forgot. Because 8 is the total number of hydrogens in the system. Okay, and how do I know it? Because it was given to me over there. Does that make sense? 8 is the total number of hydrogens in the system. That was given to me. Are we good up to this point, guys? Everything's okay? Yeah. Now, assignment. We need to assign them. If we have 3 hydrogens in the system with 1 signal, most likely that would be a CH3, right? If we have 3 hydrogens in the system, most likely that would be a CH3, and this will most likely be a CH2. Are we good up to this point? The next spectrum we are looking at will be the cozy spectrum. Now, up to this point, technically for some of you, you should be able to get what the final structure is. Because you guys already have enough information to be able to put together and imagine what the final structure is. Then use the other spectrum, the cozy, the head core, the carbon, just to confirm that the structure is correct. Does that make sense? Usually the proton NMR is largely enough when you have small molecules. The proton NMR is largely enough to determine the structure. And then you now use the other spectra just for confirmation. Is that okay? So let's look at the cozy. We need to fill this table for the cozy. I want the table to be together, so I don't have to do some work. So we need to use the cozy. Let me open my cozy. So this is my cozy over here. Again, I repeat, it might not be visible, but I guess you guys all have an individual copy. Okay? This is my cozy. Remember what we said, cozy is a combination, it's a 2-dimensional spectrum. On the y-axis, you have a proton NMR, and on the x-axis, here, you also have another proton NMR. Okay, so you have 2 proton NMR, one on the y-axis, one on the x-axis. And so what is advisable for you guys to do when you have a cozy spectrum is to label it. And your labeling has to match your proton NMR labeling. Does that make sense? And so if A is a signal closer to 0, you maintain 8. Does that make sense? So over here, this is a chemical shift 0, and that's the chemical shift 5. This is a chemical shift 0, and that's the chemical shift 5. Okay? So this first signal here is closer to 0. So that would be my A. And this will be B, and that will be signal C. Does that make sense? So I try to match that signal to my proton NMR. And the same thing over here. In this case, this will be signal A, and that will be signal B, and that will be signal C. Does that make sense? Now, when you look at your cozy spectrum, you quickly notice that there is an imaginary diagonal here that is being generated by the signal. So if you look at these signals here, you look at this one, this dot, and that dot, they lie along a diagonal. Does that make sense? And those signals, all the ones that lie along the diagonal, let me use a transparent ink. So the signals, this guy, and that guy, the ones that lie along the diagonal represent protons that couple with themselves. Does that make sense? So if you look at this first signal here, that first signal simply means that proton A couples with proton A. Yes?
You said that A was the one closest to zero?
Yes. Remember that on the y-axis, this is the scale over here. This is the scale of the y-axis, and the 0 is up, and the greater number is here. And for the x-axis, this is the 0 of the x-axis. Does that make sense? Yeah. So the protons that lie on the diagonal couple with themselves. Okay? So in this case, we'll say A couple with proton A. And if you look at here, B will couple with proton B. And over here, C will couple with C. And so because those protons couple with themselves, those signals are not very useful. Okay? They're not useful because they couple with themselves. The signals that are useful are the off-diagonal signals. And those off-diagonal signals simply represent protons that couple with each other. Okay? And usually you just choose to interpret one half of the diagonal. You can interpret the upper diagonal or interpret the lower diagonal. It means the same. If A couples with B, it means that B couples with A. Does that make sense? And what that simply means is that proton A are next to proton B. That's the meaning of being coupled to each other. So for example, when I look at a signal off diagonal, in this case, I only have one signal, this guy. That signal is off diagonal. And that signal simply means that proton C will couple with proton A. Does that make sense? That's the meaning of that signal. It means that C is standing next to A. Is that okay with everyone? So that gives you an idea about the connectivity. C is standing next to A. If you want to look at this one here, that signal that was there, that signal will still say C. What is that? That signal will still say C couples with A. What am I? Here. Does that make sense? Which means the same thing. So you can either interpret it with the green or you interpret that with the red. It all means the same thing. Does that make sense? Any question? Now we have to go back to our table and fill in the information. We need to fill in the information on the table. So signal identifier, we have three signals, okay? A, B, and C. Those are the signal identifier. The multiplicity remains the same. We've done that before. A was a triplet, B was a singlet, C was a quartet. Does that make sense? That information remains the same. Now, coupled proton identifier. We notice that A was coupled to C. Does that make sense? From the cozy, A was coupled to C. So if we go back here, we can see A coupled to C. B, was B coupling to any proton? No, so we leave that blank. And then C couples to A. Does that make sense? C couples to A. Now it's a multiplicity of coupled proton. In this case, we're looking for the multiplicity of C. The multiplicity of C, it doesn't change. C is a quartet, and the multiplicity of A doesn't change. It's a triplet. Does that make sense? Are we good up to this point? Okay, yeah. So let's go back to this table over here. According to the cozy, it says that A is standing next to C. It means that we'll have something like a CH3 and a CH2. These are proton C and these are proton A. Does that make sense? And then proton B will be standing somewhere alone. Can you see the structure already? And if you go back to your IR information, from the IR information, you already know that. Remember, there are two fragments from the IR information. There is R1, which we need to know what it is, and there is R2, which we need to know what it is. So right now, you can clearly guess that this could either be R1 or R2. And this also could either be R1 or R2. We just need to find out exactly which one is which. Does that make sense? If this group constitutes R1 or this group constitutes R1, that's what we need to make a decision. Does that make sense? That's where we need to make a decision. We need to decide which of those two groups is actually the R1. Let's fill the table for the carbon NMR. Carbon NMR, that's what we need to do. We need to fill the table for carbon NMR. Remember, the rest of the information here are mostly complementary informations now, okay? Because you already know what is happening. Yes? On the coupled proton, because it says multiplicity of coupled proton. I don't need to do that for B because B is not a coupled proton. Just C. No, I have to do it for both of them. Because in this case, the coupled proton is C, and in this case, the coupled proton is A. You see that? Now, I don't get the question.
I was thinking that you would add both multiplicity with A and C.
No. Separately. I give them separately. Yes, put them in separately. My pen is no longer writing. I don't know why. My ink is finished. So let's go to the carbon NMR. So over here I have two spectra superimposed. The first one, you can see I have two spectra. This thing is killing. I have two spectrums here. They are all superimposed, okay? The upper one is a carbon 13, and then the lower one is a depth 135. We always superimpose them. The carbon 13 spectrum will give you information about the type of carbons present in the molecule. And then the depth will also give you information, will give you further information about the nature of those carbons. How many CH3s you have in there, how many CH2s, how many CH, if any, and so on and so forth. Is that okay? And so accordingly, we also have to label. We also have to label our carbon NMR. Okay? And conventionally, I always use uppercase letter to label my carbon NMR. And I use the same rule. So the first signal, I will label it with capital A. The next signal will be a capital B. Then that will be a capital C. And this will be a capital D. Does that make sense? Now you've noticed that there is a bunch of peak signals that I actually skip on purpose. This guy here. It's a whole bunch. That's a signal for the solvent. Does that make sense? That's a solvent signal. So I don't care about that. Usually we'll tell you which one is a solvent signal. We'll let you guys know. Does that make sense? So I have a total of 4 different carbon signals here. A, B, C, D. It means I have 4 different types of carbons in there. Okay. Now when I look at my depth 135, let's look at the depth 135. Okay. Now on the depth 135, there are only 3 signals. If you notice, the signal at 0 here doesn't count. Okay. The signal at 0 doesn't count. Then there is this signal here, 1, 2, 3. Signal D is missing on the depth. Signal D is missing on the depth. And that simply means that D is a carbon without hydrogen. Does that make sense? Because C is missing on your depth, D, because carbon D is missing on the depth, it simply means that carbon D is a carbon without hydrogen. Because carbon without hydrogens don't show up on the depth. That's the first information you need to have in mind, okay? Now the next thing, if you go back to your table of reference, let's go back to our table of reference. We go to the table of reference and go over to the NMR section. Yes, if we go over to the NMR section, this section of your table of reference, it tells you that CH3 and CH will have a positive signal. Is this thing normal? Yeah, signal D is 0, meaning it doesn't show. No, no. Those are the phases. That plus, minus, and 0 represent the phases. Does that make sense? The plus, minus, and 0 represent the phases. The plus means that it's on the positive phase. The minus means it's on the negative phase. And then 0 means it doesn't show. Does that make sense? And I think there's a problem here. There's a reversal of polarity here. When I process the spectrum, I didn't reverse my polarity. But you guys will have the correct spectrum in the exam. Trust me. You guys will have the correct. So if we go back on this spectrum here, okay, normally this is the positive phase and that's the negative phase. Does that make sense? So the positive phase is above, the negative phase is below, okay? But in this case, because I have my signal with a reverse sign, the sign of my signals here are reversed. So in this case, on my negative phases, I will have my CH3s here. And then on the positive phase, that will be a CH2. But take note, this is not exactly the way it should be. It should be the reverse. The CH3s should be up and the CH2 should be down. Does that make sense? So when I was processing this spectrum, I forgot to reverse the phase. But you guys will be given the correct phase in the exam. Is that okay, guys? Yeah, that should not confuse you. So that is signal A, signal B, signal C, and so signal D doesn't have anything to show. Nothing to show for signal D. So once we have those information on the spectrum, we can then go back to the table and fill in the table, populate the table with the data. So that's the table. We need to fill in the table. I don't know, this thing has, my pen here on Microsoft Word is no longer writing. Huh? Yeah, when I hit draw, you see it's not activated. You see that? Let me close it and open it back. Well, you see, this is a different table from what we've been filling. Okay, we're back to normal. Back to normal. So signal identifier. Signal identifier, we have signal A, signal B, signal C, and signal D. Does that make sense? Those are the signal identifier for the carbon NMR. Okay? And what are the chemical shift? What's the chemical shift for signal A, guys? Remind me, I don't know. 14. B. C. and D.
170.
So the depth, under the depth, will either decide whether they are positive signals, zero, or negative signals. Does that make sense? And remember, I told you guys that my depth was wrongly processed. So normally, A is a CH3, and so A should be on the positive side. B is a CH3, it should be on the positive side. C is a CH2, it should be on the negative side of the signal. And D is 0. Does that make sense? Is everything okay, guys? Perfect, yes. Yeah, those chemical shifts. Yeah, they came from the graph. Yeah. You guys gave me that. I didn't. B, yeah, 21. 21. Thank you. Thank you for the catch. So, yes. Say that again. Well, remember I said that C is a CH2, right? Normally, I said when I process this spectrum, I forgot to reverse the phase. So in a normal circumstance, the CH3s should be on the positive phase and the CH2 should be on the negative phase. So interpreting on my table, I'm interpreting and see if I didn't do a mistake, you know. I'm not a, yeah. So you guys need to keep that in mind. And the way to know that, what will help you remember it is your table of data. You will have a table of data given to you in the exam. And that table of data will always remind you. It will let you guys know that CH3s and CH are on the positive phase, CH2s are on the negative phase, and Cs with no hydrogens have 0 signals. Does that make sense? The table of data is there to remind you about that. So types of carbon. The types of carbon, for A we know it will be a CH3, for B we know it will be a CH3, and then for C it will be a carbon without hydrogens. Does that make sense? Yes. Well, you already know the different fragments present in your structure. You already know that the CH is no longer present. It's not present in your structure. Does that make sense? So yeah, remember I said the remaining spectra, whether depth or cozy, they are kind of confirmatory spectra. They kind of like confirm what you already have. You understand what I mean? You already know what is in there, but you are just using it now to confirm what you already have. Just give me a second, please. Back to which one? Here to the spectrum?
No, I'm talking about where you said we already know we don't have to see it. Like, where do we find that?
Oh, where do we find that? That we didn't have a CH? From the proton. From the proton NMR. You remember? Here. Right from the beginning. Right from the beginning, the proton NMR tells us that we have a CH3, CH3, CH. Okay, based on the integrations. Yes.
On our exam, if we only put integral math one time, like you have the carbon on the proton.
You know the answer. I will also give you 1 time point. Right? I will also give you 1 time point. If you show it 3 times, I give you 3 times the point, right? Yeah. Just to be fair. Are we good with the depth and the carbon NMR? Yes. Are we good with the depth? Pay your debt. It's good to pay your debt. So let's go with the head core. Head core. So let's open the head core spectrum. This is my head core spectrum. And just like a proton, a cozy, the head core is also a two-dimensional NMR. Unlike cozy, which is a proton-proton, head core is a carbon-proton. And so head core will give you information on which carbon is connected to which proton. Does that make sense? So it gives you more precise information. And so you also have to label your head core. And when I look at my labeling, over here, this is my 0, and this goes up to 70. So when I have from 0 to 70, that's my 0, and that's 70. It means that the spectrum up there is a carbon NMR spectrum. Does that make sense? Okay, because I have 0 up to 70 here, it means this is my carbon NMR spectrum. And over here, I have 0 up to 5. It means this is my proton NMR spectrum. And I have to label the spectra again. Labeling is important. With my carbon NMR, this was labeled A, B, and C. With the proton NMR, this will be labeled A, this will be labeled B, and that will be labeled C. You need to be consistent with your labeling. You need to be consistent with the labeling. Does that make sense? Now, if you notice, carbon D does not appear here. Why? No hydrogens. Does that make sense? Because head core only shows carbon with the hydrogen. So because D has no hydrogen, it doesn't appear on the head core. And so according to this head core, it means head core says that carbon A correlates with proton A. It means that carbon A contains proton A. Carbon B contains proton B. And then carbon C will contain the proton C's. Does that make sense? So here we'll write it A, B, small b, and capital C, C. Does that make sense? It means that carbon A bears proton, carbon C bears C, B bears B, A bears A. Okay, that's basically what head core is all about. Okay, that's how we interpret the head core. So if we go back to our table, we need to fill those information in on the table here. So carbon identifier. On the head core, we're able to identify 3 carbons, A, B, and C. And then we're asking for their carbon NMRs. The carbon NMRs remains the same. 14.27, 21.063, and 60.269. Now, correlated proton. Correlated proton. We're able to find that A correlates with small a, B correlates with B, and C correlates with C. Does that make sense? What are the proton NMR chemical shift? That's what is called PMR, the proton NMR chemical shift. So the proton NMR for A, what is the chemical shift of A? 1.21, 1.97, and 4.0. 1.21, 1.99, and 4.0. Was that one? I think I'm right? And so the table of head core is there, clean. You have it there. Question? Anyone? Any question? Anyone? I'm ready to take. Yes. Head core? Well, this is a small molecule. When you have a bigger molecule, you really appreciate it. Here, the purpose is the exercise is mostly for you guys to be able to interpret it. When you have a molecule that's a little bit bigger in size, that really helps you to connect the carbon to the hydrogen easily. Huh? No, to know which one is R1, R2, it will be the chemical shift. It will be the chemical shift, the exact value of the chemical shift. Well, that's why we tell us which one is R1, R2. Why do we do it? Because we have to teach you guys how to interpret the head core. Because in the future, you guys might see a molecule that only head core will be able to help you get the correct structure. And in that case, you already know how to interpret the head core.
What she's saying for this molecule, even what did this show us for this molecule?
It shows us that for this small molecule. So these were hydrogen A. And so this carbon is carbon capital A. And so these are hydrogen C, so this carbon is carbon capital C. These are hydrogen B, so this is carbon capital B. That's basically what head core is telling us here. Okay, that's just what we'll be able to retain from head core. But when you have really a large system, trust me, it's very useful. Very, very, very super useful. Now we need to propose a structure. These are the fragments that we have present in our structure. Those are the fragments that we have present in our structure. So we need to propose a structure. Now, we need to see, that's what chemical shift and the chemical environment becomes important. R2 is connected to an oxygen. It means that R2, the carbon or the hydrogen of R2 will be deshielded. Does that make sense? It will be deshielded, it means it will have a high chemical shift compared to the ones that will be connected to the carbon. Does that make sense? Compared to the one that will be connected to the carbon. And so, when you look at your proton NMR, or the chemical shift of your proton NMR, what am I here? A, B, C, which one is the most deshielded? C. Okay? Because C is the most deshielded, it means that C is most likely the one connected to the oxygen. Does that make sense? Because the most deshielded will have a high chemical shift. Is that okay, guys? The most deshielded will have a high chemical shift. So C is the most deshielded. So chances are that C is the one connected to the oxygen. So I will have my C here. And we already know that A has to be next to C. And so my R1 would be proton B. That would be my structure. Does that make sense? That would be my structure. So I will call this one proton C. Proton B, proton C, and proton A. Carbon A, carbon D, carbon C, and carbon B. Does that make sense? So that would be my structure. This guy is called ethyl acetate.
Didn't you say like protons A, B, and C would bond with the carbons A, B, and C respectively?
You see, sometimes I don't know what I do. Yeah, sometimes I don't know what I do. So this guy is called ethyl. Woof. I took 55 minutes to solve this because I was explaining it to you. I will just look at the proton NMR of this thing in 2 seconds. I will give you the structure. Like just looking at the proton NMR and I tell you it's ethyl acetate. Huh? Really? I already know it. Remember, I'm the one who created this question. So I already know the answer. So 2 seconds might be too much for me. Because it's my question. I didn't say somebody will create a question for me. Yes, it's my question. Yeah. So does that make sense? So you guys can do it. So practice it. And I think during your lab for tomorrow, Wednesday, and Thursday, you will have another opportunity to fill a table like this. Okay, you will have another opportunity. Yes. She said on the test. She said on the test. Yes, Shelby. Oh, on the test. Okay. If you go back to, I think, the table of data that I gave you, if you look on the table of data below, there's another problem similar to this one, very similar. And so with this one, the IR is given to you, so you can use the IR to fill the information. The formula of the molecule is C8H16O2. Do you see that? With this one, the formula of the molecule is C8H16O2. The IR is given to you. The proton NMR is given to you. The depth and the carbons are all given to you. Does that make sense? The COSY is given to you. And then the HECO is given to you. And so you can practice again on your own and fill this information and come out with a structure. I will be seated in my office and I will take it as a challenge. You are welcome to come and show it to me. You are welcome to come and prove it to me that you know what you're doing. Does that make sense? Yes. Say that again. Any question? So you have an extra exercise to practice on your own, right? So, any question? Because you will see it on Friday at 6:30. It will be there looking at you. Yes. Chapter 5. Let's go to chapter 5. No, but the homework is due today, so we need to finish chapter 5 and then you guys do the homework. The homework is due today, right? I think it's due at 11 o'clock today. You didn't know that? So let's do chapter 5 so you guys can go and finish your homework. Chapter 5 is not difficult. No, okay. I will extend the dates. Oh, follow up. I will extend the date for the homework for chapter 5. But chapter 5, you guys, we've done chapter 5 last semester technically because all you need to do in chapter 5 is the nomenclature and the stability of alkenes. Nomenclature and stability of alkenes. So that's all we have to do for chapter 5. It's not much. It's something that will take us about 10 minutes. So on Thursday, before we start a general revision for the exam, I will have to go through chapter 5 first, which will take us about 15 minutes or so. Okay? Then I will extend the homework for chapter 5 probably, I don't know yet, probably through the weekend. Okay? And chapter 5 is not part of the exam. The exam is only NMR. Does that make sense? Exam is only on NMR. Oops, what am I showing? That's not chapter 5. I don't want to leave you guys go for 15 minutes like that. It hurts me. I cannot do that. No, trust me, I cannot give you guys just 15 minutes free like that. I have my textbook here. Let's look for a problem on the textbook and solve. Trust me, I will never leave you guys go. I will never give you guys 15 minutes. I can give you guys 2 minutes, but not 15. No, not 15. 15 minutes is too much. Huh? Well, you guys don't have a... I didn't post the slide for chapter... Did I? I don't think I posted a slide for chapter... Yeah, chapter 5 is not... Yeah, I forgot to post it because I knew it would not be a long one. Because I knew it would not be a long one. Let me see. Let's look at chapter 5 very quick and then we'll get done with that, okay? And then save our life and move forward. So chapter 5 is the chemistry of alkenes. Okay. Chapter 5 is the chemistry of alkenes. And then alkenes are molecules are unsaturated. We refer to them as unsaturated hydrocarbon. It means that they contain at least a double bond or a triple bond. In this case, we'll be looking at a double bond. Okay. Now, the general molecular formula for alkanes. Remember when we did that, we said alkanes had a general molecular formula of H2N plus 2. But in this case, the general molecular formula for alkenes will simply be CnH2n. Okay? CnH2n. That's the general molecular formula of alkene. So if I give you a molecule and you want to determine if that molecule is an alkene, if it satisfies this molecular formula, then chances are that the molecule is an alkene. For example, if I give you a molecule, let's say C2H4, does C2H4 satisfy the molecular formula CnH2n? Yes, it does. Because if carbon equals 2, then the number of hydrogens should be 4. So C2H4 is an alkene. That's how you can determine an alkene using the molecular formula. Is that okay? Now, the degree of unsaturation, which is the total number of pi bonds and rings in the system. We've talked about that already several times. Degree of unsaturation is a review. And you remember the formula for the degree of unsaturation. 2C plus 2 minus the number of hydrogen minus the number of halogens, all that divided by 2. You've seen this formula before, guys, right? Several times. So that formula just gives you, this is X. X stands for the halogens. It could be chlorine, fluorine, or bromine. Okay? And so whatever you have from this calculation tells you how many pi bonds and how many rings you have in the system. Okay? And I'm sure we'll do some examples together. Does that make sense? So saturated versus unsaturated hydrocarbons. Alkanes are referred to as saturated hydrocarbons because all the carbons in alkanes are sp3 carbons. Since all the carbons are sp3, we refer to them as alkane. Now, when you have sp2 or sp carbons, sp2 or sp carbons in a molecule, that molecule usually will be referred to as unsaturated hydrocarbon. So meaning double bond or triple bond will be referred to as unsaturated hydrocarbon. Does that make sense, guys? Nomenclature for alkanes. Remember that in this nomenclature, all the rules that you guys learned for nomenclature applies for the alkenes. Okay? And with the alkenes, we simply replace the suffix ane of the corresponding alkane to ene. Does that make sense? And so in this case, ethane, which is the first alkane, ethane, which is the first alkane, will be replaced and that becomes ethene. Does that make sense? And all the rules of nomenclature applies here. All the rules of nomenclature, whatever we've done, meaning that identify the longest chain and so on and so forth and so forth. Those rules apply. Is that okay? And so if we want to name this molecule, there are two ways we can name the molecule. 1, 2, 3, 4 carbons or 1, 2, 3, 4 carbons. Okay? You choose the direction that will give the double bond the smallest number possible. That's just the direction you choose. And so in this case, I will go from, what is it? From left? Is it left? Yeah, from left to right. In this case, I will go from left to right because the double bond in this case will be on carbon 1. So because I have 4 carbon, that will be a bute. And then I need to give the position of the double bond, which is position 1. So this will be referred to as 1-butene, meaning the double bond is connected on carbon number 1. Over here, we'll have 2-butene because the double bond is on carbon number 2. No matter the direction you start counting, the double bond will still be on carbon number 2. And so the molecule will be referred to as 2-butene. Okay? Now, we have a bigger molecule over here. The molecule is made up of 6 carbons. Molecule is made up of 6 carbons. So because it's made up of 6 carbon, it will be a hexene. And now we need to give the position of the double bond for the hexene. Okay? And you choose a direction that will give the double bond the smallest number. This thing is about to die. Question so far with nomenclature. Choose the direction that gives the double bond the smallest number. And so in this case, the double bond will be on carbon number 2. So the molecule will be referred to as 2-hexene. Okay? Molecule will be referred to as 2-hexene. Now, we have a specific case over here. In the alkene, your longest chain must always be the one involving the double bond. Does that make sense? Your longest chain must be the one involving the double bond. If I have this molecule, I can count 1, 2, 3, 4, 5, 6, 7, 8. That's technically the longest chain. But that longest chain does not involve the double bond. So I need to choose the longest chain that involves the double bond. And the longest chain that involves the double bond here will be made up of 6 carbons. Does that make sense? The longest chain that involves the double bond is made up of 6 carbons. That's why we have the name hexene. And now we need to give a position to the double bond. We now need to give the double bond the smallest number possible. In this case, it will be number 1. So it will be called 1-hexene. And so the remaining group, which is this group here, will now act as a substitute. And that group is made up of 3 carbons. So that will be a propyl group. 3 carbon stands for prop. And those 3 carbons are connected to carbon number 2. So that's why it's referred to as 2-propyl. Does that make sense? So that will be 2-propyl, 1-hexene. Question. Stereochemistry of alkenes. Alkenes, we have 2 types of stereoisomers. Okay, the cis, trans, or the E and the Z. You already know those things. I told you guys, chapter 5 is things that you know. Okay, 2 stereochemistry, the cis, trans, and the E and the Z. The Z means the same size. It means the hydrogens on the same side. That's the Z. That is a type of cis. And then the E, the hydrogens are on opposite end. That gives you the E isomer. Okay? And then the next thing I want you guys to know about this thing is the stability. Between the Z and the E that we have on the board, which one is more stable? Okay? The E is more stable. The E is more stable because the groups are placed opposite each other. Does that make sense? The bulky group are far away from each other, so it makes the E more stable. So it makes the E more stable. Now, in a molecule where you have more than 1 double bond, we have to use the prefixes di, tri, tetra in order to identify the number of double bonds we have in the system. For example, if we have 2 double bonds in the system, that system becomes a diene. A di means 2 double bonds. If we have 3 double bonds in the system becomes a triene, just like what we have over here. And we have to give numbers to all those double bonds. So this guy will be called 135. It means I have a double bond on carbon number 1, a double bond on carbon number 3, a double bond on carbon number 5. So this will be 135 hexatriene because that we have 3 double bonds. Okay? This other guy here will be called 1,3-pentadiene, meaning I have a double bond on position 1, which is over here, and another double bond on carbon number 3, which is there. That's why it gives me 1,3-pentadiene. And the other guy will be called 2,4-heptadiene. Or is it diene or triene? Heptadiene, meaning I have 2 double bonds. So the diene stand for 2 double bond, and the triene stand for 3 double bond. And you have to give their position. Okay. So we continue with the nomenclature. In terms of nomenclature, number the chain in the direction that gives the functional group the lowest number possible. And so we've talked about that one here. And that's an example. The functional group in this case is a double bond. And so we have to number the chain, make sure we give the double bond the smallest number possible. Okay. So we have 2 chains here. We can have a chain 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. Or either way. So either way, the name of the molecule remains the same. Either way, the name of the molecule remains the same. I will call it off here, and then we'll continue. We'll finish it off. The remaining section is just a little bit, because I have to talk about the stability, and that's it. I will talk about the stability, and that's it. So you should be able to start the homework for chapter 5 and most likely finish it.